Hello and welcome to Programming Like It's 1979. Today we're going to continue our look at gamified logic. Last week I showed you the natural number game, which used a web browser version of the Lean Proof Assistant to prove theorems about the natural numbers. In talking about this on Twitter, I mentioned a different gamified browser game called the Incredible Proof Machine that I said has not gotten the attention it richly deserves, and that made me realize I should talk about it here. The Incredible Proof Machine is the brainchild of one Joachim Breitner. He's an excellent teacher. He's taught a few online and offline Haskell courses. I've taken them. I really enjoyed them. This is a project he did to introduce high school students to formal proofs. And the way he did it is particularly brilliant. Let's just dive in and take a look. So there is a link to the paper he wrote describing the Incredible Proof Machine, which I encourage you to read if you're interested in learning about what went into making it and kind of his philosophy behind it. So as we look at the front page, you can see that the work or the games are divided into different sessions. The sessions, generally speaking, get a little harder, but also introduce new concepts as we go along. And this is it looks like a fairly vanilla form of predicate logic of the type that you would have been introduced to in any logic class. All right, let's get to the proofs. Given A, prove A. That's what this means. Before we begin, let me make this a little easier to read. So you can move these blocks around. And once you've moved them around, you can either zoom in using these plus and minus buttons. You can, I don't know what 1 to 1 mean. I guess that means the original scale. Or you can just click fit. That makes it so that basically all the blocks you have on this canvas will fit on screen, which makes them a little larger. All right, we have A, we'd like to prove A. Well, we just drag out our line here and plug it in. Couldn't be simpler. That's our first level. This is trying to just introduce the mechanics of dragging and connecting. All right, so let's look at our next level. Well, here we have 2 predicates and 1 goal, A. So let's make a mistake here and see what happens. I'm going to pull out B and plug B into A. We get an adorable little skull and crossbones here. And what we can see is that this line turns red, so we know it's wrong. And it also tells us why it's wrong. This side of the line closer to our goal says it wants an A. And this side of our line closer to our predicate says it has a B. Well, B is not A, that's why this doesn't work. And this is part of Breitner's philosophy of allowing and even encouraging mistakes. You want students to experiment. Mistakes are how we learn. I'm sure that during the course of this very video, I'm going to make a bunch of mistakes. The important thing is to make the mistake and try and figure out what that means. All right, so we can hover over the line. We get a nice big red X to remove it, and we can plug our A into A. That's our solution to that level. All right, given A and B, prove B and prove A. This just teaches us that our wires can cross. And I called them wires, but really they're lines. You can drag a line around. In fact, I'll probably be doing that. I know my face is in the corner here. In fact, it's blocking this right now. So let me move that over there. And now we can actually see. These are logical lines. They are not actual wires. There's no electricity flowing here. You can make these as complicated and baroque as you like, and it's not going to affect the validity of the proof. So organize them as you see fit. Now we're going to introduce our first introduction rule. We've got A and we've got B, and we want to prove A and B. And the and symbol here is this little caret here, this little up-facing caret or circumflex. This gets to one of my very few criticisms of the Incredible Proof Machine. It's clearly intended to be used in conjunction with an actual class, with a teacher who is explaining what all these little symbols mean. I understand that and respect it, but if you don't have that, there's really very little context in here. There is some help. There's this page here that talks a little bit about what these characters mean, but not in any kind of detail. So if there's one thing I could have had, I would have loved to be able to have every block have a little eye or a question mark on it that explains what that block is. For example, this right here, this block with 2 inputs and 1 output and a picture of the circumflex, that is the AND introduction rule. It's going to take 2 propositions, in this case A and B, and it's going to output a third proposition, which is the proposition A and B, or the expression A and B. It would be great to have that identified somewhere as the AND introduction rule, rather than me having to recognize it from my class or from reading. All right, so that does solve that level. As I said, this first level is going to go super fast. Given A, we want to prove A and A. Well, this level is going to teach us that we can wire the same proposition up to multiple inputs. Let's make my video a little smaller so that I'm not always in the way of these propositions. Given A and B, prove A. Well, now we're going to introduce, pardon the pun, another block, which is the AND elimination block, which of course is implementing the AND elimination rule. That says that if we have A and B, or X and Y, or any 2 things, we can get the individual items out of them. In fact, this is a good opportunity for me to show you another aspect of the UI here. Let me disconnect this link. Okay, so now we have the block. As I pull out these things from the block, we can see it says X and Y. And when I plug in this A and B, they change to A and B. So this, again, is part of Brightener's really aggressive, wonderful commitment to encouraging the user, encouraging the player to make mistakes and try and learn from them. Given A and B, prove A and prove B. Well, we're just going to use the AND elimination rule again. And here we're learning that ordering matters. We've got an A and we've got a B, and that means that the A is going to come out of the top output and the B is going to come out of the bottom output. Given A and B, prove A and B. I think the point of this level is to teach you that even more complicated expressions, if you have the expression midway through the proof, or in this case at the beginning, you're done. Given A and B, prove B and A. Well, aren't those the same thing? No, they're not the same thing. And that's what this level is teaching you. Order is important. So how are we going to swap these things when we don't have any kind of commutativity rule at this point? Let's use an AND elimination and an AND introduction. So our A is going to go to the bottom, our B is going to go to the top. That gives us B and A. Now here's my question. We just proved AND commutativity. But there's no AND commutativity block. I literally just said that. But that seems like a useful thing to have around. I don't remember. Can I somehow make this a custom block? I see this thing down here that says custom blocks. I finally read the documentation, and it turns out that if you shift-click your blocks, you can then add a custom block. So I'm going to go ahead and add this block here. There's a little snowman there. I'm not sure what that snowman means. I didn't see a way to change it. Let me try that again. Shift-click. So if I wanted to make a custom block, it looks like it just gives it an arbitrary name. I don't see a way to change the emoji. But if I want to create, for example, a commutativity of conjunction block, I can now do that. So that's great. All right, given A and B and C, prove A, B, and C. This is just going to be stacking up a few AND eliminations and making sure I keep track of what is in which output. And that's pretty straightforward. Everything is in the order in which it goes into the blocks. Only 2 more levels left in the first session. Given A and B and C, I'm not going to say parentheses. That's A and B. That's that. Prove A and C. So we need, again, a second AND elimination. We only need the A from here, and then we need an AND introduction. And note that with a few exceptions, which we'll talk about later, it's perfectly fine to leave outputs unused. As long as you can get to the final proof state, it's all good. All right, our last level. Given A and B and C, prove A and B and C. Do you like how I'm saying the pronunciation out loud just through tone of voice? That's acting. That's talent. It's inborn and practiced together. I've honed my craft over many, many years. All right, let's eliminate that first AND. I think we're going to have to eliminate the second AND as well, and then we're going to have to introduce 2 ANDs. In fact, we know that programmatically because there's 2 ANDs in the final expression. So this is going to be a little confusing. I apologize. I'm going to go backwards. This gives us A and... Okay, so here's another great thing. I just started working this proof backwards. There's a really talented professor, James Aspnes, who has these notes on discrete math. And his advice for proofs is that you should start at the beginning and work forward, and simultaneously start at the end and work backwards. And then when you meet at the middle, pretend that you'd been working forward the entire time, like you intended to do it that way. So that's what this allows us to do. Working completely backwards, we've now said, here, let's take out all of these other. Okay, so I have this proposition floating in space, not connected to anything, but the machine knows that I'm trying to prove A and B and C, and therefore it knows that we need to prove A and we need to prove B and C. And so now I could literally just try things out until I find where A actually fits in our proof. That's pretty cool, I think. So this is going to be B, and this is going to be C. And that's it. That is the first session of Joachim Breitner's Incredible Proof Machine. I did forget to say this at the beginning of this video. You can find the Incredible Proof Machine at the URL incredible.pm. It should work in any browser that supports JavaScript. I encourage you to try it out yourself. We are going to continue. This is going to be a little bit of an unusual week for us here at Programming Like It's 1979. We're going to do a bunch of videos on this today, trying to burn through really as many sessions as we can. It's a long weekend, so I'm going to make the best possible use of it. I will see you in the next video, Session 2. This has been Programming Like It's 1979. Thanks.